Welcome to The Explainer. Today we're diving into something we all use literally every single second of the day, but rarely stop to think about. Every time you flip a light switch, charge your phone, or turn the key in your car, you are tapping into a massive, complex history of energy transformation. But where does it all actually come from? Today, we're not just looking at your standard power plants. We are embarking on a traceback journey to uncover the ultimate, real-world origins of the energy that powers our modern lives. Right off the bat, the global energy consumption data paints a pretty stark picture. Roughly 85% of our current world energy still relies entirely on fossil fuels. We're talking coal, oil, and natural gas. Then you've got hydroelectric power sitting at about 7%, nuclear at 4%, and a surprisingly tiny 4% slice for other renewables like wind and solar. We talk a whole lot about the green transition these days, but this breakdown tells us exactly where we stand right now. The reality is our global infrastructure is still overwhelmingly addicted to fossil fuels.
So, here is our roadmap for this journey. We'll start with the sun's energy monopoly, move into stored sunlight, harnessing wind and water, the non-solar outliers, electricity mechanics, and finally wrap up with nuclear fusion. Let's jump right into Section 1, the sun's energy monopoly, specifically direct solar power. It's honestly mind-blowing when you think about it, but almost every single drop of energy we use traces back to just one fairly average star located 150 million kilometers away. The sun basically has an energy monopoly on Earth. The heat and light we get from it take about 8 minutes to travel through empty space, and our most direct way of actually catching that power is through arrays of solar cells, photovoltaic cells. We use these to transfer the energy of sunlight straight into electricity. It literally produces a voltage the moment light hits it. It's totally clean, zero emissions. But as you can probably guess, there's a catch. This power source completely drops to zero the second the sun goes down, and it's highly dependent on the weather. So to make it work 24/7, we absolutely need massive panel areas and incredibly robust battery storage. Moving right along to Section 2, stored sunlight, looking at biomass and fossil fuels. Because we can't always guarantee the sun is going to shine, humanity has relied heavily on the Earth acting as a giant battery, storing all that solar energy over time. Now, before we go further, we have to establish the difference between renewables and non-renewables. A renewable resource is simply one that replenishes naturally as we use it. The wind is going to blow again, the sun is going to rise tomorrow. Non-renewables, though, they are essentially single-use on a human timescale. Once we dig them up and burn them, that's it. They're gone forever. The whole difference really just comes down to how fast the Earth's battery can actually recharge itself. So how exactly do those non-renewables form? Well, fossil fuels are essentially a massive time capsule. When you burn a lump of coal, you are literally releasing sunlight that was trapped by trees in the Carboniferous era. We're talking over 300 million years ago. Those ancient plants captured solar energy through photosynthesis, eventually died, and sank into swampy ground. Because there wasn't enough oxygen down there, they didn't completely rot away. Add millions of years of immense crushing pressure, and they turned into the highly concentrated underground reserves we mine today. It's literally ancient stored sunlight. But then you have biomass. For example, if a Maasai tribesman uses animal dung to start a fire, they're also releasing stored solar energy. But there's one huge difference here. That energy was stored only in the very recent past, maybe a few weeks ago for the dung, or maybe 100 years if you're burning a tree. Because we can easily just grow another tree or harvest more dung relatively quickly, biomass is firmly in the renewable category, even though the underlying mechanics are pretty much exactly the same as fossil fuels.
Okay, Section 3, harnessing wind and water. Let's talk about kinetic weather energy. You might not immediately connect a massive gust of wind or a raging river to a star millions of miles away in space, but the physics connect them perfectly. The sun actually heats the Earth's atmosphere really unevenly. Warm air expands and rises up, and then cooler air rushes in to take its place. That convection current, that's what we call wind, and we use it to spin those massive turbines. On top of that, the sun's heat evaporates ocean water, which eventually falls as rain on high-altitude ground, filling up rivers and enormous hydroelectric reservoirs. So by driving both the wind and the entire water cycle, the sun is indirectly giving us all the kinetic energy we need to generate huge amounts of clean electricity. All right, now for a real plot twist. Section 4, the non-solar energy outliers: tidal, geothermal, and nuclear. Up until this exact moment, every single thing we've discussed has been solar-powered in some way. But there are 3 rogue energy sources that want absolutely nothing to do with the sun. First up, tidal energy. This relies mostly on the moon's gravitational pull, literally dragging the oceans back and forth, and we can trap that moving water behind huge barrages. Second is geothermal energy, which taps directly into the internal heat of the Earth itself, heat that's kept alive by the radioactive decay of rocks deep underground. And third is nuclear fission. This involves splitting massive, heavy uranium atoms that have been buried in the Earth's crust since the entire solar system formed 4.5 billion years ago. No sunlight required for any of these.
Moving into Section 5, generating electricity. Let's look at the mechanical core of it all.
So we've sourced all this raw energy, but how do we actually turn a pile of black rock into the electricity that's powering the device you're watching this on? A glowing uranium rod doesn't just magically charge your phone on its own. We need a mechanical translator. And the core architecture of most power stations around the world, whether they're gas, coal, or nuclear, is actually remarkably similar. It's this beautifully elegant, multi-stage process of converting one type of energy into another, over and over, until we get that electrical output.
The whole thing really boils down to a 3-step logic. Step 1, you burn the fuel, or split the atom, to create massive amounts of thermal energy, boiling water to make high-pressure steam. Step 2, that high-speed steam blasts into a turbine, converting the thermal energy into kinetic mechanical movement. Step 3, the spinning turbine turns a generator. And this is where the real magic happens. By spinning conducting wires inside a magnetic field, you induce a voltage. That process, electromagnetic induction, is the literal birthplace of the electricity flowing through our grids today. Now, when we're trying to figure out the future of our power grid, we have to look objectively at the facts. It is a massive game of trade-offs. Solar and wind, amazing, zero emissions, but they're inherently unreliable because we just can't control the weather or the rotation of the Earth. Coal, on the other hand, is highly reliable. You just toss more in the furnace when you need it, but its carbon emissions are actively driving climate change. Then there's nuclear, highly reliable, zero carbon emissions, but it leaves us with dangerous radioactive waste that lasts for millennia. The hard truth is, there is absolutely no perfect, consequence-free power source currently sitting on our grid.
And we really can't ignore the physical footprint here either. It all comes down to energy density. Fossil fuels and nuclear power are insanely concentrated. Just one relatively compact nuclear or coal station can power a city of 100,000 people. Wind and solar, by contrast, are extremely dilute. To replace that single coal plant, you might need to install 50 to 100 wind turbines spread out over 20 square kilometers of land. So transitioning to renewables isn't just about inventing new tech. It requires a complete, massive reimagining of how we use the physical landscapes around us. And finally, let's look ahead to Section 6, the future and the promise of nuclear fusion. We've spent almost this entire explainer talking about tracing our energy back to the sun. But what if we didn't have to? What if we could just build our own? Unlike the nuclear fission we use today, which tears apart heady, ancient atoms, the sun makes its power through nuclear fusion. It takes two tiny, light hydrogen nuclei and forcefully smashes them together to form a heavier helium atom. Because the final mass is slightly less than what you started with, that tiny missing bit of mass is converted into a staggering amount of energy, thanks to Einstein's famous E equals mc squared. But to overcome the natural repulsion of those atoms and force them together, you need extreme, mind-bending conditions. We're talking roughly 15 million degrees Celsius.
Which brings us to the ultimate question. Can we actually pull this off? Can we build a miniature sun right here on Earth? Well, with massive international engineering projects like ITER in France, scientists are using gigantic magnetic fields inside machines called tokamaks to trap plasma that is literally hotter than the core of the sun. If we can achieve sustained net positive nuclear fusion, we would unlock a clean, zero-carbon source of virtually unlimited energy without any of the long-lived radioactive waste of fission. It is, without a doubt, the hardest engineering challenge humanity has ever taken on. So the question I'll leave you with today is this. Will we solve this artificial star puzzle in time to finally cure our addiction to fossil fuels, or are we going to run out of time?